The last line is the theorem, which states the equivalence of categories between some crystalline representation of GK over some coefficient field. And the category of filtered phi mergers, which is weakly admissible over some coefficient ring, and I think it's K0 tensor space E. Here. This is proved by, I would like to remark that this equivalence, I have several remarks about this equivalence. The first one is it is proved by firstly by Fontaine and Colematz and Fontaine. But after that, there are several other proofs is obtained. First by Fontaine, yes, by using some so-called almost CP representations. And his idea is more has a more sophisticated interpretation by Colematz and also by Farag and Fontaine. And this is some notion of finite dimensional vector space. Yeah. Where? Microphone? Oh, yes. I don't know how.
Probably there's two normally. You normally wear two, right? One for recording and one for.
I have two devices, but
no,
let's switch it off.
Yeah,
it doesn't work. Oh, okay.
No, but it's speaking.
No. Can you hear me?
No.
Oh.
No, I don't think so.
No?
I think it's this one.
Let's switch it on.
Yeah. I don't know.
Maybe battery is out.
Yeah, maybe the
okay, I'll try to make as lot of those out loud here as possible. Yeah. It seems that it doesn't work.
Oh, this one. Test. This one. This one is okay.
This one's okay.
This one.
저 마이크가 문제. 이거는 리프링 마이크고 저기.
그것도 좋아요.
네.
Okay. Let's continue.
리프링 마이크.
Very nice. Yes. There are two other proofs obtained. One is by Fontaine, and it is. What happened? The other one is obtained by Kissing. Oh, it doesn't work? Oh. Okay.
1 minute.
1 minute. 1 minute. Yeah. Okay. Yeah. And the other proof is obtained by Kissing and Belger by using some theory of phi gamma measure, which I explained yesterday, but the coefficient ring is different, and over the Roth ring and the theory of Kedlayer concerning some slope filtration of the phi gamma module over the rubber rings. And also another remark is that there exists a variant of the theorem for semi-stable representations and for the round representation. Okay. Thank you very much. The round representation is yes. And both this is classified by some phi gamma. I don't know, filtered phi module. No, phi n modules. Another structure which is an endomorphism n, and which also we impose the condition of weak admissibility, weakly admissible, and also the round representation correspond to some weakly admissible filtered and phi and n, and also another action of the Galois group action phi n GK module, but this action factors through the finite portion. And the base field is this is over K 0 tensor with E, but it is a larger field and maybe some K0 Arithmetic station. Yeah. Well, and next I would like to explain the Fontaine-Lafayette theory. Which gives a classification of the representation which is only linear of GK, which is crystalline, and which means the first subcategory of all representation, and whose object is T, a representation T such that its base change to E is crystalline. And then the theorem of Fontaine-Lafayette says that there exists an equivalence of category between the crystalline representation over OE, but whose Hodge state weight is between 0 and p minus 2, is equivalent to the category of some so-called category of strongly divisible mergers and of some Hodge state weight between 0 and p minus 2. And I will explain its definition and its object. It's a finite generated free module over WK tensor with OE over CP. equipped with some filtration by several modules, and such that the decreasing and field 0 is equal to the 4m, and field the p minus 1 is equal to 0, and also it is equipped. I'm sorry, I have forgot to suppose an important assumption. Suppose that K is unramified over QP. Yeah? Oh. Okay. And the semi-linear endomorphism M, satisfying some conditions, which is sigma semi-linear. Sigma is a Frobenius endomorphism of delta K. Such that the image of field I is divisible by p to the I, and M, field IM is saturated in M in the sense that it's coconal. M over field I is torsion free. And the next condition is that the image of phi, image and the phi of field I M over p to the I, and take a sum over I is equal to the entire M. And this equivalence can be realized by using the ring A crease, which I have introduced yesterday, in a way similar to that we define the function decrease by using decrease. Okay, and then next we talk about the importance of why these subclass of representation, the RAM and crystalline or stable representations, why the RAM or crystalline. An answer is that if the representation V comes from a geometry then V is wrong. Yes, it comes from the geometry means that it comes from some Galois representation given by taking a Talco homology of the motifs over K. So more precisely, the following conjecture is for. Then, any answer? And Fontaine made several conjectures, which is which are now proved and called C drum and C crease and C stable, and whose statement I will record now. And C-drum, yeah. Yes, it is the statement that follows that suppose that xk is a scheme which is separated and of finite type over k, then its étale cohomology group x k bar qp is a de Rham representation. And it's and the d de Rham of this representation is isomorphic to some algebraic de Rham cohomology of x over k as a filtered vector spaces, which is defined by by taking hypercohomology group of the Rham complex when x is smooth, and in the general case it is defined by Hodge one. And it is proved. Same is the conjecture, but it is now theorem. It is proved by four things. When x is proper and smooth over k, and smooth. I think, and also by Carton, Tsuji, and Fontaine. I think maybe Carton, Tsuji. And for some cases, maybe many people concerned proved by Tsuji is main case, and Yamashita in general cases. Maybe, and an alternative proof is obtained by Beilinson in general case. And as a corollary, we have some following Hodge state decomposition. Corollary. And suppose that x is proper and smooth over k. Then the i's cohomology, étale cohomology, tensors with Cp, the completion of an algebraic approach over K, is isomorphic as Geller module to the Dirac sum of the cohomology of the sheaf, coherent sheaf of differential modules, differential forms. Tensors with Cp and taking some Tate Swiss, I think it is -3. With respect to the action of Gk, where the action of this cohomology of Gk is trivial.
So when you don't write a subscript on the cohomology if that's just a top cohomology?
Oh, yes. I'm sorry, yeah. I should write it down and it down. Thank you very much. And the second result is that let's see, Chris, which is constructed by Fontaine and proved by unknown. All things is not this one. This is proved by Fontaine. And coupled and Fontaine nothing. And some restriction. Nothing and coupled. And Suzy. In this case, we assume that X is proper and smooth and having a good reduction. So that X is a model of Xk is a proper and smooth over OK. Then the tau cohomology is crystalline. And it's the Chris is isomorphic to the crystalline cohomology. Darwin, where Y is a special fiber of X. Oh, and W is down, okay? This is isomorphic as in filtered. Over K0. The phi action is on this side. It's defined by crystalline properties, and the filtration on this side. Oh no, this is K0. And filtration on this side is given by the comparison between crystalline cohomology and the round cohomology, and then Hodge filtration on the round cohomology. Here. And the third theorem is in some sophistication of this theorem. Rated proof 1 4. It is called conjecture C stable. And its assumption is that the X is a semi-stable proper and smooth variety, proper and semi-stable. And fixed by a uniformizer pi, okay, which is used to define the ring B stable and also define a comparison between some crystalline cohomology and the RAM cohomology. And then in this case, the tau cohomology group, Caper, it's semi-stable. And if you take the stable, then it is isomorphic to some cohomology group called log crystalline cohomology of some pair of Y is a special fiber S as before, and Y is the log structure, and which is a log structure is a sheaf of monoids with homomorphism from My to Oy, satisfies some conditions. I will not explain here now. But, this log structure is a pullback of the log structure of X corresponding to that here, corresponding to the normal crossing divisor. Defined by spatial fiber. It's over W and some log structure. This is written by L. This log structure is some very stupid log structure associated to the pre-log structure from N to W, which goes 0 to 1 and 1 to 0. And tensor with K0. Which is an isomorphism of filters phi n modules over K0, where the phi is again a crystalline properties of the low crystalline cohomology, and n is in some monodromy operators defined by Hilder and Kettle, and also by Hilder. And this infiltration also given by the comparison between low crystalline cohomology and the RAM cohomology, which depends on the choice of the uniform matter pi. And also there is some more sophisticated theorem, 2.5, which is, I don't know its name, but it is proved by Yamashita in the... Oh, this one?
Yeah.
Oh, yeah. This one is proved by Tsuji. But situation is a little complicated, but let X is the same as theorem before, is a proper, which has same stable reduction. And suppose that we are given a normal crossing divisor, a relatively normal crossing divisor, and it is horizontal. Horizontal means that it is some smooth. It's locally its components. Its reducible component is locally smooth. Okay. And also it's a normal crossing to Y. Y is a spatial fiber. I have not explained what is semi-stable, but semi-stable means that it's done locally, and X is isomorphic as an open subscheme of and spec or K and a polynomial ring. You have any T1 time the product of some part of coordinates is equal to the uniformizer. Yes. And this condition means that eta locally, if you take in more and more eta locally, then the divisor is isomorphic to some product. The one equation is the product is equal to 0. The variable is this variable and this value is disjoint. And we assume moreover that D is the sum of two effective divisors, and such that D1 and D2 do not have a same irreducible component. And we denote by C the special fiber or D. And since we have assumed that D is a horizontal divisor, so it is a normal crossing divisor of special fiber, and it is also decomposed by C1 and C2, the sum of C1 and C2. And under this assumption, the statement is here.
Horizontal means that the generic special fibers have the same dimension.
Yeah. More precisely, it is smooth over the piece. Its irreducible component is smooth, locally smooth. You know. I have everything. And under this notation, the cohomology group, which is compactly supported along D1 and without support condition along D2, and which is defined to be the hypercohomology group, escaper of the J1 lowest link and our J2 part, lowest of QP, where escaper in J1 means SK1 minus D1, and J2 means escaper minus D. K. It's semi-stable, and it's the ST is isomorphic to the similar object and along similar kind object in the log crystalline side. Why? Here. Which is defined to be a K0 tensor space of W of a log crystalline cohomology. More precisely, which is a limit over N of H I log cris or something, and my is here my is a log structure, which is a pullback of a log structure. And it's associated with that divisor D plus Y. And over the same face. Oh no, sorry. The coefficient is different. Coefficient is Kc1. Kc1 is something like a crystalline analog of the ideal sheaf corresponding to the device C1.
Explain about this decomposition, D1 plus D2, what is it? Is it arbitrary or
It's arbitrary here. We just tell here, but this is technically important in the proof of the theorem. Then in the remaining time, I would like to explain the proof. There are several proofs of the conjecture sheet RIMS increases known by one uses an almost total theory developed by p-adic, and the other method is by using so-called symptomic cohomology. It is developed by Fontaine in Messing and Kato in Tsuji and Yamashita and something. And there are several other methods, for example by Nizio by using K group and by Billingson another different method by using some derived Durham complex. But we would like to explain the proof of theorem 2.5. Which is proved by using some symptomic method. Symptomic complex. And I'll try to prove it here, down here, and let R is in any integral domain of characteristic P. Then the P power map with the endomorphism ring. And this induces endomorphism denoted the same symbol on its ring of bit vectors by functoriality. Then since the invariant part in R under F is isomorphic to FP, so the invariant part of WR and F is isomorphic to WFP, which is isomorphic to CP. And because that the ring increase, we can construct. We have described the ring increase by using some ring of bit vector of R for a very special kind of R. And for increase, we have a similar isomorphisms, but it's more of some twisted version. Which is as follows. That we do not by fill R sub P of A cross is submodule of the ring A quiz. Of elements which belongs to the field R of the realm and satisfying the condition that its image and phi is divisible by p to the r in A quiz. There R is, maybe R be allowed. There R is equal to 0 case. Then we have a short exact sequence, P t to the r divided by some integers, p to the q times q factorial, where q is an integer product of r divided by p minus 1. As gamma module, this is a state twist, R state twist of trigger characters. And the middle one is field R. Now, the right side there is an increase, and the map is given by the 1 minus phi over p to the r. And this is exact. And this, we interpret this as there exists a quasi-isomorphism between the complex p over A quiz, 1 minus phi over p to the r, A quiz, and this complex of length 2 is isomorphic to some state twist, R state twist. This we denote by the B R prime. Yeah, please give us this resolution. Yes. This is something like an object in the tau side. Let's recall that A quiz is defined to be a crystalline cohomology of something. So it is something on the crystalline side. So this is this is short exact sequence is some resolution of something in the tau side by something in the crystalline side, and we use this idea more higher dimensional over an object in higher dimensional varieties. And we obtained in the crystalline side in the sun is some object, very strange object called atomic complex. X is also in expert. It is called a atomic complex. Atomic. Atomic means some property of morphism, which is locally completed the section of that. This definition, but atomic is similar kind of complex first introduced by Montaigne and Messing by using some site and taking cohomology on the site called atomic site. But the definition of atomic complex doesn't use that atomic site just by using some one special atomic morphism and using some complex computing crystalline cohomology, and it is an object in the derived category on a special fiber. I'm sorry, maybe this expand me the YK bar. Z over P is modules, where n and r is an integer, non-negative integer, and n means the coefficient is a Z over P to the n, and r means something twist. And by definition, this object can be constructed by using some complexes computed crystalline cohomology. So it is easily related, it can be easily related to the crystalline cohomology. So, and we can obtain a map from the cohomology, a tau cohomology, of this complex, and taking a projective limit over n and tensor base QP, which we got by symptomic cohomology, over, and some VSD over H of crest I, Y, C1, C1 shrink, and C2 oyster. Yeah. Well, VSD is an inverse of the functor, quasi-inverse of the functor in the equivalence categories. I'm sorry, I forgot the tape twist. Tensor with DSD in the tape twist, R's tape twist. And more precisely, VSD. D is just D phi is equal to 1 and take an intersection to the field 0 of the tensor with K. And also there is another, yes. And we want to relate the crystalline side and the tau side, so we have to construct a map. Yeah, this part is also not so difficult, but the difficult part is this part, and we can construct.
What would VST?
What
is V?
VSD, the definition is here.
Oh, I see.
And this is a quasi-inverse of the function VSD. I'm sorry, n is equal to 0, and n is 0. We can construct another homomorphism, a map, and from the symptomic complex to the sheaf of Minerva cycles, and R, J, 2, J1, demonstrate R, J2, oyster, Z over P to the N, which is by R, where I and J is an inclusion of spatial fiber. Okay, K bar, an inclusion of generic fiber. Yes, it's cohomology over the spatial fiber computes the étale cohomology of the generic fiber by the property exchange theorem. And then we can show that after some truncation, yes, so the degree from 0 lower at most R, so it is almost an isomorphism. This map.
So you are always asking why
Uh-huh. Yes, yes. Oh, it's outside in a special fiber. Here, this map is almost a quasi-azimuth. Almost means that the co-counter and co-counter is bounded independently of n. Yeah. Under this restriction, we need to take R sufficiently large to prove this comparison theorem. And this statement is the technically most difficult part. It is obtained by using an intensive study of the cohomology shifts. On both sides. And I think this part with having originated in the calculus computation of the higher dimensional cross field theory, and its outside it is done first by Brock and Kato by a paper which is different from that on Tamagawa number conjecture, and by I think Hyodo. And the atomic side, it is done first by Kato in some case, in a good reduction case, in a paper p-adic cycle, and by Kurihara over there, and by Tsuji. Yeah. And technically, it is the most complicated part of the proof. This induces a map better from the atomic cohomology to the entire cohomology, D1, D2, roster, R, maybe take R, which is an isomorphism for sufficiently large R. And so we need to, and to prove the theorem that we need to define the map of comparison between the beta combined, alpha combined the inverse of beta is a map of comparison. Is an isomorphism. But to prove that, we need there is a technique by using a cup product, and so it's sufficient to show that an alpha and beta is compatible cup product. And for alpha, it is easy, relatively easy. And for beta, it is not so easy, and we need another technique. Which is called a hollow log scheme. Is used to prove that beta is compatible with cup product. And then taken by air. Yes. Then this shows that this is a comparison map, and then so this gives an isomorphism between the stable of these guys and this stable of the Italian homology, and it's isomorphic to this one. So, and this is an outline of the proof of the comparison theorem by using atomic complex. And today I want to stop here.